Have you ever wondered what happens when a massive star exhausts all its fuel? Well, to understand this, we need to take a step back and look at the life of a star. Picture a gigantic star, a cosmic furnace burning fuel in its core. This isn't a one-off event, but a constant process. Stars are like the universe's most diligent workers, tirelessly burning fuel day in, day out. This burning process creates an outward pressure, a sort of push that counteracts the inward pull of gravity. So imagine a cosmic tug-of-war, a ceaseless battle between two forces. On one side, you have the outward pressure pushing everything away from the core. On the other side, you have gravity, tugging everything inward. Now this equilibrium, this cosmic stalemate, changes when a star exhausts its nuclear fuel. As the fuel burns out, the outward pressure decreases because there's no more fuel to burn. It's like one team in our tug-of-war suddenly losing their strength. But gravity, the relentless force that it is, doesn't take a break. It doesn't yield or show mercy. It keeps pulling inward, squeezing the star tighter and tighter. It's as if the other team in our tug-of-war just gained a massive advantage. This shift in balance, this tipping point, is where things start to get truly fascinating. The star, deprived of its fuel, now has a weakened outward pressure while gravity remains as strong as ever. The question then becomes, what happens next? What occurs when gravity, unopposed and unyielding, gets the upper hand? This is where we delve into the heart of the Oppenheimer-Snyde model of gravitational collapse. This is where we start to unravel the mystery of what happens when a star, in its twilight moments, exhausts all its fuel, and the scales tip in favor of gravity. So, what happens when gravity gets the upper hand? This is where Oppenheimer's collapse model comes into play. Oppenheimer, a brilliant physicist, came up with a fascinating insight about what happens next. Picture this. A massive star has exhausted its nuclear fuel. The cosmic furnace has run out of coal. The outward pressure decreases because there's no more fuel to burn. But gravity, that relentless force, doesn't take a break. It keeps pulling inward, squeezing the star tighter and tighter. Oppenheimer's groundbreaking insight was to recognize the implications of this unyielding gravitational pull. As the star's fuel supply dwindles, its core begins to collapse under the immense weight of gravity. Imagine squishing a balloon in your hand. As you apply more and more pressure, the balloon becomes denser. Similarly, as the core collapses, it gets denser and denser, and gravity becomes even stronger. But here's where things take a turn for the mind-boggling. As the core collapses, it doesn't just get denser, it also releases a tremendous amount of energy. This energy bursts forth in the form of neutrinos, elusive particles that zip through matter with little interaction. These neutrinos, like cosmic heralds, shoot out from the collapsing core, carrying away with them a significant amount of energy. Now let's revisit that cosmic battle between gravity and pressure we talked about earlier. With the energy carried away by the neutrinos, gravity gains the upper hand. It's like the final round of a cosmic boxing match, and gravity just landed the knockout punch. The outer layers of the star, no longer able to resist, start falling inward faster and faster, like a skyscraper imploding. However, the core's collapse is just the beginning. The star's destiny is yet to unfold. As the core becomes denser and the gravity becomes stronger, a point of no return is reached. We call this the event horizon, and what lies beyond it is a black hole, one of the most mysterious phenomena in the universe. But the collapse of the core is just the beginning of our story. As the core collapses, something mind-bendingly cool happens. Picture the core of this massive star, shrinking under the relentless pull of gravity. As it condenses, the core becomes denser and denser. And within this cosmic crucible, a surge of energy is released in the form of neutrinos. Now, neutrinos are no ordinary particles. They're tiny, almost ghost-like, and they hardly interact with matter. This means they can pass through almost anything without being affected. And as the star's core collapses, these neutrinos dart away, carrying with them a significant portion of the star's energy. This is where the cosmic scales begin to tip. Remember that epic battle between pressure and gravity we talked about? Well, as these neutrinos escape, they take with them the energy that was helping maintain the star's outward pressure. And with this loss of energy, gravity begins to gain the upper hand. The outer layers of the star, bereft of the pressure that was holding them up, start to succumb to gravity's pull. They begin falling inward, speeding up as they go, like a skyscraper collapsing in on itself. This is gravity's victory lap. But this isn't just about gravity flexing its muscles, it's also about the transformation of energy. The star's original energy, once used to maintain pressure and fight against gravity, is now being carried away by neutrinos. The energy isn't lost to the universe, it's simply changing form and location. So what started as a titanic struggle for balance between pressure and gravity ends with gravity emerging victorious, pulling the star's outer layers inwards. This is the fascinating process that Oppenheimer's collapse model helps us understand. A star, once a beacon of light and energy in the cosmos, now stands at the precipice of a dramatic transformation. With the energy loss and gravity's victory, we're one step closer to the formation of a black hole. This is the thrilling journey we're on as we delve into the mysteries of the universe and the birth of black holes. So, what happens when gravity becomes so intense that nothing, not even light, can escape? We've reached the climax of our cosmic drama. The core of the star, now incredibly dense and compact, is under the unrelenting grip of its own gravity. The outer layers of the star, having lost their energy to the fleeing neutrinos, are falling inward at an accelerating pace. It's a bit like watching a slow-motion replay of a skyscraper collapsing, only on a cosmic scale. As the core continues to collapse under its own gravity, something extraordinary happens. The core becomes so dense, and the gravitational pull so intense, that a boundary forms around it. This boundary is known as the event horizon, a term that sounds like it's straight out of a science fiction novel. But this is science fact, not fiction. The event horizon is a point of no return. It's the ultimate cosmic boundary. Anything that crosses the event horizon, be it matter, light, or even time itself, can't escape the black hole's gravitational pull. It's swallowed up, forever lost to the known universe. Now, beyond the event horizon, we find the heart of the black hole. It's here that the star's core has collapsed to an infinitesimal point of infinite density, known as a singularity. The laws of physics as we know them cease to apply at this point. It's a place of mystery and intrigue, a place where our understanding of the universe is pushed to its limits. And so the death of a massive star leads to the birth of a black hole. The star's life may have ended, but its legacy continues in the form of a black hole, a testament to the power of gravity and the fascinating complexities of our universe. And that, dear viewers, is the essence of Oppenheimer's collapse model, the cosmic dance of gravity, pressure, and the mysterious ways of the universe.